You ever stop and think about how, water just magically appears at your tap, or how fuel gets into your car? Well, the answer, most of the time, is this hidden workhorse you've probably never even seen. It's called the centrifugal pump, and today we're going to pull back the curtain and see how this amazing, simple device literally makes our modern world go round.
So just how big of a deal is this thing? Get this, a staggering 80%, that's right, at least 80% of all pumps used in big industries are centrifugal pumps. So yeah, the water you're drinking, the fuel in your car, if it's a liquid that needs to move, chances are this is the device doing the moving.
So, how are we going to break this down? First up, we'll cover what this thing even is, the world's unseen workhorse. Then, we'll get into the secret language engineers use, something called head. After that, we'll see what happens when the pump meets the system. Then, things get dramatic with a pump's worst nightmare. And we'll wrap it all up with why this matters for all of us in Smarter Pumping, Smarter Planet. Let's get into it.
Okay, let's dive right in. Section 1, the world's unseen workhorse. So what is this thing, really? Okay, at its absolute core, a pump has one simple job: to add energy to a liquid, right? It takes the spinning power from a motor and basically just shoves a liquid from point A to point B. That could be pushing it uphill against gravity or just getting it moving through a whole maze of pipes.
But how do we actually measure that energy? You might think, oh, horsepower or maybe watts, right? Nope. Engineers have their own special language for this, a term that is absolutely key to understanding everything else. And that term is head.
So let me ask you, how would you measure the energy a pump adds to a liquid? The most common answer is pressure. And that makes sense, but here's the thing. Pressure only tells you part of the story. In fact, it can be super misleading. This is where head comes in. Now, head is the total energy the pump gives the liquid, but, and this is the weird part, it's measured in units of height, like feet or meters. I know, it sounds strange, but think of it this way. Imagine a pump is like a slingshot. Head is the amount of energy that slingshot gives to a stone. A powerful slingshot gives the exact same amount of energy to a tiny pebble as it does to a heavy rock. It's the same idea with a pump. It provides the same head, the same energy, no matter how dense the liquid is. And this is why head is so incredibly useful. Just look at this. Let's say you have a pressure of 1,000 psi, okay? That pressure can hold up a column of water that's 2,310 feet high. That's insane. But take that exact same pressure and try to hold up a column of mercury, which is way denser, you only get 170 feet. See? The pressure is identical, but the work being done, the energy, the head is totally different. Head tells us what the pump is actually doing. Okay, so we've got it. A pump provides head, which is energy. Simple enough. But here's the thing. A pump never works in a vacuum. It's always connected to a whole system. Pipes, valves, tanks, the whole shebang. And this is where the real magic and the real complexity starts.
Really, the best way to picture this is like a matchup. On one side, you have the pump's performance curve. You can think of this as the pump's personality. It's just what the pump is capable of. And on the other side, you've got the system head curve. And that's the job description. It's what the system is demanding from the pump.
So first let's talk about the job description, the system's demand. Just to lift the liquid from point A to point B, you need a certain amount of energy, right? That's your static head, the baseline. But then, the moment you start pushing liquid through the pipes, you get friction. And the faster you try to push, the more that friction pushes back. It fights you. So when you draw a picture of that increasing resistance, boom, that's your system head curve. All right, now for the pump's personality. Every single centrifugal pump has this fundamental trade-off. It's a classic you can't have it all situation. It can create really high energy, a lot of head, but only if the flow rate is low. Or it can move a ton of liquid, a really high flow rate, but only with low energy. It absolutely cannot do both at once. And that trade-off right there is its performance curve. So here's the cool part, the magic moment. When you put that specific pump into that specific system, where is it going to run? Well, it's going to find its own happy place. It will naturally settle at the single, one and only point where what the pump can do perfectly intersects with what the system demands. That intersection is the operating point. It's the sweet spot. Okay, every hero has a kryptonite, right? And for our humble workhorse pump, there is a villain that can literally tear it to shreds from the inside out. We're talking about a pump's absolute worst nightmare. So what do you think it is? Really high pressure? Some crazy corrosive chemical? Nope, it's none of those. The single biggest killer of pumps, is something you'd probably never, ever guess.
Vapor bubbles. Yep, that's it. Bubbles. But hold on, we're not talking about air bubbles. We're talking about bubbles of the liquid itself turning into a gas. It happens if the pressure at the very entrance of the pump drops too low. The liquid just spontaneously boils, even if it's completely cold. It's like boiling water, but without adding any heat. Wild, right?
So to stop this from happening, engineers have this supercritical safety number they live by. It's called net positive suction head, or you'll just hear it called NPSH. The easiest way to think about it is this. The pump requires a certain amount of pressure at the inlet to stop that boiling. Let's call that NPSH required. The system, in turn, has to provide at least that much pressure and hopefully more. We'll call that NPSH available. As long as what's available is greater than what's required, you're golden. No bubbles.
And actually figuring out how much NPSH is available, well, that's a whole puzzle for engineers. You can see from this diagram, they have to juggle everything. The pressure from the atmosphere, how high the liquid is, the friction from the pipes. It's a really delicate balancing act to get it right.
So what happens when that balancing act goes wrong? What happens when the pressure that's available drops below the pressure that's required? Well, that's when the pump starts to cavitate.
And wow, just look at the aftermath. It is absolutely brutal. Here's what's happening. Those nasty little vapor bubbles form right at the center of the spinning impeller, where the pressure is lowest. But as they get flung outwards, the pressure skyrockets, and those bubbles collapse with unbelievable force. We're talking about thousands of tiny, powerful underwater explosions going off every second. And they physically chip away at the metal, just eating the pump alive from the inside out.
All right, so we've gone deep on head, performance curves, and the absolute nightmare of cavitation. It's all really fascinating engineering for sure, but why should you care? What does this all mean for the real world? Well, it all comes down to one single, hugely important word: energy.
Get this. Pumping systems account for a massive chunk of all the electricity used by industry worldwide. It's huge. So every single time a pump is the wrong size, or it's running inefficiently, or God forbid it's cavitating, it is just hemorrhaging energy. So, understanding all this stuff isn't just for engineers trying to keep the pumps from breaking. It's about building a smarter, more sustainable planet for all of us.
And the good news is, we have much smarter ways of doing this now. Instead of just running a pump at full blast all the time and using a valve like a brake pedal, we can use variable speed drives to give the pump only the exact power it needs. We can get way better at right-sizing pumps for the actual job instead of just slapping in something that's way oversized. And sometimes it's more efficient to use a team of smaller pumps that can turn on or off to meet demand instead of one giant energy-guzzling one.
When you really break it down, the centrifugal pump is the perfect example of the incredible, invisible engineering that's all around us all the time. Understanding it kind of gives you a new appreciation for the complex, hidden systems that make our world work. And it really makes you wonder, doesn't it? What other unseen workhorses are out there, quietly powering our modern lives?